about probably when we come back from Thanksgiving, we'll be like 2 weeks away from the end of class. So I'm going to ask you for an update to show me you've completed some progress by the end of the week, and so I'd hope that you guys could like write me a short note, like saying, hey, I did some stuff, because this is time's running out. But anyway, assignment 4 is going to be a written assignment, not so much a programming assignment. So that will come out tomorrow or Wednesday, and it will just be written, but it won't be quite as big as the others. You can still use your late days, you can still do whatever you want, but it will be less insane. Okay? Or maybe the others weren't insane. I don't know if that's the right word. Okay, any news? Anything going on in the world? Yes.
IBM hit 50 qubits.
50 qubits. Tell me what that means.
They have a quantum computer that can handle up to 50 bits of information. And previously, the record was around 20.
Good. So what's a qubit?
It's much like a normal bit, except it's quantum, which means it doesn't have a discrete state. It has some sort of superposition that collapses.
Good. So in normal computers, we have a register, and inside the register, we have gates, and those gates can take on either a 1 or a 0 position, and that's how normal computers do computation. If you want to brute force, let's say hypothetically, you want to brute force a cipher, you create a register that has 128 bits in it for the key, and then you would go through, and let's say you have a plain text and a ciphertext, you'd build an AES circuit. This is just a kind of a straw man version of how you might do this. Let's say you have an AES circuit, and you'd have a key register, which is 128 bits long, hypothetically speaking. You'd wire this together, you'd have a plain text that you knew, and you'd have a ciphertext you knew, and then you'd have something in here that would basically, encrypt and output like, 1 or 0. This is my brute forcing machine I've just built, and basically you'd go through from 0, 0, 0, 0, 0 key all the way up to 1, 1, 1, 1, 1, 1 key until you tried every single key. And of course this sucks, you would never do this because in practice there are 2 to the 128 keys, and brute forcing would take you an enormous amount of time, even if you had a massively parallelized version of this. But what if you could test all the keys at the same time? What if you had a register that the individual bits didn't just have to be in a 0 or 1 state, but they could be in both states at the same time? And you had some way, and this is the very hand-wavy part, where these individual bits could be in all possible 2 to the 128 states at the same time, and you had a way to make this system resolve such that it was much more likely when you connected this to the rest of the universe that these would actually resolve to a state that was the correct solution to this problem rather than just some random key. And so roughly speaking, we have a couple of algorithms that we know how to run that you can run on a quantum computer, but we don't have really feasible quantum computers. Anyone know what those algorithms are and why they're significant? Anyone? Yes. Shoot.
Shor's algorithm is one of them.
What does Shor's algorithm do?
Shor's algorithm breaks public key cryptography.
Good. Shor's algorithm is an algorithm for what specific problem? Factoring. Good. And what's significant about it is that if you have a quantum computer, it runs in probabilistic polynomial time. There's actually a complexity class for this, but we'll say it's a polynomial time algorithm on a quantum computer. If you have a large enough number of qubits in your computer, you could run this algorithm today on RSA keys. It would take several thousands, maybe even tens of thousands of qubits to actually do this. And as you just mentioned, we only have quantum computers that appear to work on 50 qubits at a time, and they only work for 90 microseconds at a time because they have to be kept in this incredibly delicate state and they fall apart very quickly. So we have Shor's algorithm that can to solve the factoring problem. There's a variant of Shor's algorithm that can, fortunately, solve the discrete logarithm problem, which is actually very closely related. And then also, and we haven't talked about this yet, but the elliptic curve version of the discrete logarithm problem. All of these things exist. If we can build enough qubits and get a quantum computer working that actually implements Shor's algorithm, pretty much all the public key crypto we use today is toast. And it just turns out that IBM's up to 50 qubits. So this is a really bad sign for us. We need better algorithms that can survive the coming, maybe 15, 20 years from now, practical quantum computers that will break all of our public key crypto. So that's kind of scary. Anyway, it's scary, but it's good because quantum computers are constructive. They can do other stuff too. What's another algorithm you can run on a quantum computer? Anyone know? Useful for crypto, that is. Anyone? Anyone heard of any other quantum computer?
Grover's, but I think you already covered that with the discrete log problem.
Well, Grover's does something different. So Shor's is a specific algorithm or set of variants of algorithms that solve these number theoretic problems. And it just happens to be that these problems work very well because there are certain ways you can cancel out some answers and you can get them to work. There's another more general algorithm, which is actually a search algorithm called Grover's algorithm. And the interesting thing about Shor's algorithm is, as best we know, it takes you from a super polynomial time, what we believe the best time you can use right now that we know of, the best algorithm we know of to solve these problems in a classical computer is super polynomial time, in some cases exponential time. But Shor's takes it from this super polynomial down to polynomial time. Grover's algorithm is a search algorithm. It's very useful for things like brute forcing keys, but it's not as much of a breakthrough in terms of time complexity. Basically, if you want to search through a key space that is 2 to the n bits, well, Grover's algorithm basically will give you the square root of that. So basically, it will divide, if you want to put it another way, instead of taking 2 to the 128 to search through AES keys, it would take you 2 to the 64 operations if you had an appropriate quantum computer using Grover's algorithm. So Grover's algorithm is also very significant, but not as devastating, because if we want to deal with Grover's algorithm, we can just use a 256-bit key, or double all the sizes of our hash functions or whatever. And so Grover's algorithm doesn't kill us, but right now, Shor's algorithm and its variants are really scary. So this is bad for us. And why is it particularly bad? Why do we need to care about this today, even though we don't have quantum computers that actually work? Yeah.
Retroactive attacks.
Okay, explain what that means.
So there could be some, this goes back to the beginning of class, there could be some entity which is recording communications and then retroactively goes back.
Good. So what's that entity?
A nation-state adversary.
What's that?
A nation-state adversary.
A nation-state adversary. So somebody who is making recordings of interesting crypto conversations done over fiber optic cables, for example. There's a bunch of those people out there. Maybe they can't break the crypto today, but if they had like a big facility located somewhere like Utah where they could store this stuff for years and years, they could go back in time and they might be able to break communications if they keep the ones that are really interesting to them. When they have quantum computers in 20 years, they could go back in time and break these things. So there's this kind of problem, which is that, yeah, it's unlikely that anyone has a quantum computer today, but we still have to think about them, because for things that have very long shelf life, which is a very small number of things, but for things that have very long shelf life, we do care about quantum computers even today. These things are a big deal. And they're coming along. Has anyone heard of a company called D-Wave? What does D-Wave make?
Right now they're building cloud accessible quantum computers.
And their computers have thousands of qubits, right? Maybe you've seen their...
I've seen some of the literature on it, but I couldn't speak to it.
Okay, yeah.
So they've tamed back their claim that it's a quantum computer these days a little bit.
Yeah.
But the point is, they're not a quantum computer. They can't run any quantum mechanical algorithm. The thing is, in classical optimization for anti-hard problems, there's a technique used called simulated annealing, where it's kind of like the Monte Carlo, Markov chain Monte Carlo, where you parachute in the Amazon and look around. And then with quantum annealing, you're able to stop simulating the annealing and sort of just more brute force it. So it can provide a lot of speed improvements to optimization for.
Right, so they have a specific kind of quantum computer that can't run Shor's algorithm, can't run Grover's algorithm, but can solve this one very specific kind of problem that they've optimized for. And theoretically, you can reduce other problems to this, but not efficiently. And it's not even clear that their computer's faster than just running it in a classical computer and using the best known kind of algorithms that exist. So if you hear anything about D-Wave, they have been making all this fuss about having quantum computers, but it's not clear that they're really comparable. It's like the difference between Coke and Diet Coke. That's a terrible analogy. Okay, good. So quantum computers. Anything else going on in the world?
So I was able to hit a conference last week down in DC called SciCon, and there was a paper presented there on quantum computing. To be honest with you, I was in a room not understanding everything that was going on with that conversation. But the one thing that came up that I did kind of catch was the idea of using spooky action at a distance to distribute key material.
Yeah.
Which brought us right back to that classical one-time pad. The reason why we don't use it is we can't get the keys out there. But if we've got a foolproof, uninterceptable way to distributing keys.
Good, yeah. So we'll talk about this a little more later. I'll actually show you how these protocols work. But there is this thing, this whole area called quantum key distribution. And the idea, if you know any little thing about quantum physics, the idea is this. So you know that if you measure a particle, you change the state of the particle, roughly speaking. So if we run a fiber optic cable between the two of us, and I shoot photons down that fiber optic cable, the idea is that if somebody tries to intercept those photons and actually measure them, before they reach you, they're going to screw with them, they're going to mess with them. And so we can actually use that by sending photons that have different polarization and different, different like basically settings. I can send you what is effectively a stream of random bits, such that you will get those random bits. We will share the random bits by basically splitting the beam. I can send you one half of the beam, and we can basically have a bunch of entangled particles where I can measure the state and you can measure the state. But if somebody else measures the state, it will scramble the data. And so we can use that to share what is effectively a one-time pad key. And now that we've got a one-time pad key, which we can very, very efficiently set up now because of this fiber optic cable, we can then just encrypt data in the classical way, and we get information theoretic security. And so these solutions are viewed as like one hypothetical solution to quantum computer problem. They're not really a solution. You still have to build cables everywhere, although I think there's a Chinese satellite that's trying to do this with lasers in space now. So there's people who are trying to deploy this stuff. But we'll talk about how it actually works later. It involves filters and a whole bunch of other stuff. But basically, QKD is one possible solution to this post-quantum world we might go. Good. Awesome. Yeah, so there's lots of people trying to do this. What else happened in the universe? Yeah.
The Intel ME crack
Oh, yeah.
Oh, jeez, yeah.
via USB, JTAG over USB.
JTAG over USB. Explain all of these terms.
So the Intel management engine is a CPU inside of your CPU that runs Minix.
Awesome. Okay. So you got a CPU inside your CPU. It runs Minix, and what can you do with it?
You can use it somewhat like a TPM. It can do stuff that's below the OS, that is invisible to it. It can verify firmwares.
So if you own the Intel management engine,
You own everything.
you own everything on the computer. I see. Okay. And so it turns out that by connecting to USB,
Yep, there's JTAG, which is like a debugging interface for CPUs that you can own the
you can
ME.
completely take over the machine, and then everything else becomes broken. Okay, so that sounds really bad.
Yeah.
Yeah. Okay. So that's a problem. I don't know what to tell you about that.
Yeah.
Except that we use these Intel CPUs everywhere, like submarines, like all over the place. So that sounds like a really big problem. Yes.
I've certainly seen exploits, or maybe not even exploits, but reports of people who've been able to disable the management layer here and there.
Ah. Okay.
And that's like a desirable thing, considering some people don't want to have someone controlling like what their CPU does.
Right. Right.
And
Yeah, I've heard that you can set jumpers sometimes, but I don't know how to actually do it. I have no idea. Yeah, these things seem like a big deal. I mean, we make the assumption that we trust the processors we run on. So we write software, we do our best not to screw it up, and then we run it on hardware, and we hope the hardware is not broken. But it turns out that there's layers and layers and layers of stuff below our hardware that we really have to trust. What about RAM? Do we trust RAM? Can we trust our RAM? Right, so let's say we forget about Intel. Can we trust our RAM? Is it going to actually store the data we want it to store, and is it going to give it back to us? Yes.
I think that's the kernel's problem. Typically, the kernel, at least between processes, the kernel is responsible for telling you when you're trying to access some other process's memory.
Okay.
That works.
So how do we? Okay, just tell me quickly, in a security modern computer system with a memory management unit, how does the kernel keep me from writing into your process? If I get an Amazon virtual machine, and you've got another Amazon virtual machine running on that same physical piece of hardware, what keeps me from writing data into your virtual machine and then taking over your app and just totally hosting it? What security, what is happening there that prevents this from happening? Like,
There's some sort of hardware exception. Is that a seg fault? Is that?
okay, so you've all had seg faults. Please tell me you've all experienced a seg fault in your life. What is a seg fault caused by? What is happening there? What does that mean?
You're trying to read or write outside of your playpen of memory.
Okay, what is a playpen of memory?
So I'm fudging this a little bit, but it says, all right, out of the total RAM that I have available, I'm going to allocate this, I'm going to give it a separate address space, and I'm going to tell that process, okay, you can only write within this address space, and if you need more, I'll give you more, but you've got a leading, you've got a start and an end period, and then it maps that to physical memory.
Okay, so in the olden days, and in embedded devices today, we had access to actual physical memory, which would like start at 0 and go up. You know, I had a Commodore 64, and when you programmed a Commodore 64, this is showing how old I am, you would spend a lot of your time writing basic commands like peek and poke, which would like actually flip, you know, bytes of memory in specific ways, and there were exactly 65,000 something bytes, and you could touch any one of them. It was a single process machine. It was sucked, and that's how embedded devices are today. But thankfully, we mostly don't worry about that on modern machines. When you actually start up a program, that program is isolated from all of the other programs. At least the RAM is isolated, and it's done using what piece of hardware? There's actually some hardware in there that does all the things you just described.
The MMU?
Good, there's an MMU, Memory Management Unit, and it's an actual physical chip, and what it does is it creates basically an abstraction. It creates this idea of logical memory, and so the bits and the bytes in your pointers actually point to the logical memory, and the MMU maps pages of your logical memory to locations in the physical memory. And this is great because if you've got lots of programs running, among other things, it means these pages don't have to be contiguous. They can be spread out. You don't have fragmentation problems. That's nice too. But also it gives you security. If your program tries to write outside of a place in its logical memory that's actually been mapped to a real physical page, wham, seg fault. And seg faults are typically the result of like a bad pointer in a program. Okay, good. So the MMU is what gives you process isolation, gives virtual machines isolation, keeps programs from writing into other programs and changing, keeps people from writing into the kernel and like upping their privileges to make themselves a root process, right? So this is great. So we have this. Now, do you trust that this works? If the software in the operating system and the MMU work correctly, can you trust that nothing you write into this RAM is going to somehow overlap and mess with something else in RAM? Why not? Why not?
Can you trust the kernel?
Let's say we trust the kernel. Kernel's just a piece of software,
Okay.
and it basically tells the MMU, hey, program 1 is running. Program 1 only gets to access these physical pages, can't access my kernel memory, can't access these other processes, lock them out, throw a seg fault if they try to access it, and let's just say the kernel does that right. Kernel does that right. The MMU does everything right. Do we trust the RAM anyway?
Can I trust that the device is physically secure?
Sure. This is a software attack. You've got a bad piece of software on an Amazon machine, and it is trying to mess with RAM that is not its own. Do you feel safe about this? If the MMU does its job, is everyone safe? And the kernel's not screwed up. I mean, there's loads of bugs in kernels, but let's skip that. Can we trust our RAM? Is there anything you can do in software that would allow you to write to somebody else's pages? Yeah.
There was the rowhammer attack.
Okay, explain that.
So, because DRAM is not perfect, it's basically a bunch of capacitors.
Mm-hmm.
There was an attack that basically meant if you charged and discharged really, really quickly over and over and over again in one row, you could affect the rows near it.
Good. Okay, and why? Why did that happen?
Why would writing to this row of, let's say, 32 bits, 64 bits maybe, affect the row below it? Why would that happen? Physically. It's an EE answer, not a computer science answer.
Because you've got a little bit of an electromagnetic field around each one of these transistors and capacitors as it fires, and it has a small effect on the things around it.
Okay,
Now,
that's definitely part of it. The other thing about this is when you think about DRAM, think of it the way like a CRT display works. You basically got these capacitors, they get charged up, and like and every now and then they have to be painted. Something has to come across. There's a grid of wires. You don't have one wire running to every single one of these capacitors. You have a grid of wires with like an X and Y. And so something has to come along and paint them by sending a jolt of power. So when you write to this row, what you're doing, I mean roughly speaking, I'm no EE. What you're doing is you've got a bunch of wires here. You're sending a jolt of power to this wire, a jolt of power to this wire, and that sums up to be a big jolt here. That charges the capacitor. So you're actually scanning, you know, like this to repaint or to change the values of these things. Let's say I want to write it to 0. But at the same time, you're also sending power to all of these other columnar wires. So you're sending power to all the capacitors in the RAM, just not as much power as to the ones you actually want to write to. Most of the time, that's fine. But if you write a lot of times to this particular row here, you can occasionally flip a bit in a row that's adjacent because of the way DRAM works. And if you can flip a bit in a row that's adjacent, what does that mean? Who cares about that? Why is it a problem?
You can control memory, and you can also figure out where you are in physical memory.
Possibly, yeah. If you know something about the way memory is laid out, maybe my program is allocated this page, and maybe this page belongs to the kernel in physical memory. Normally, you should never know about this because the MMU is supposed to isolate you from this. But if you go here, and you can send a lot of writes to here, occasionally you can like flip one of these bits to 1. If this happens to be a variable that says, does process number 1 get administrative privileges, then you can actually cause the kernel. You can actually flip bits in state in the kernel, and if you're very lucky, you can actually make the kernel give you higher privileges, and wham, your process now has all sorts of control. If it's crypto stuff that's happening, let's say this is a secret key, and you can induce faults in the secret key, meaning flip bits in the secret key. Sometimes you can use those faults to actually learn the rest of the secret key. By getting the person to encrypt or decrypt using a slightly damaged secret key, you can leak information that can actually allow you to do very powerful stuff. Okay, so we can't trust our Intel processors exactly, and we can't exactly trust our RAM. What can we trust? I don't know what we can trust, but this is the big issue. We can do everything right in software, and hardware can still screw us up. And we're sort of learning this as we go. This is a very hard problem to solve. We don't know what to do about it. I mean, eventually we'll make better hardware, but right now we're just learning all of the different ways that security systems can break. Okay. Any other stuff going on in the world? Yeah.
Well, there was another move for the responsible encryption.
Oh, good. Yeah, I wanted to talk about that.
Great. So I mean, so we have the mass shooting followed by days of nothing happening, and then the FBI says, "Hey, let us into this. Give us a back door." And they specifically seem to have chosen to let those days pass that they could not use the person's thumb or fingers to get into the phone.
Good. Okay, so we've talked about this a couple times, right? So the FBI wants to get to your phone, and Apple can't help them. Why can't Apple help them? We did talk about this, right? We totally boringly talked about this, right? Because there's a piece of hardware in there that Apple doesn't have control over, that basically decides when you get in. And there's this thing called Touch ID. I guess we're gonna have Face ID soon. And this thing basically controls whether or not the phone will unlock. For some reason, the Justice Department waited 48 hours, even though they had the guy's fingerprints. They chose not to open the phone. And it seems like they're making a big push to have some kind of voluntary backdoor.
I've seen discussion on this and also the San Bernardino thing.
Yes.
That the FBI appeared more interested in trying to establish a precedent than they were actually getting the intel off the device.
Yeah, and it doesn't seem like there's going to be any intel on this, right? Like, it's not like a guy had a bunch of accomplices. This is a lone shooter, really tragic, horrible thing, but like, what's on the phone? How is this going to help us? It doesn't seem very likely that it will. But there's been a big push, a lot of newspaper articles where people are trying to the FBI seems to be trying to push this very hard, that this is a big threat to us. So yeah, I don't really know what to say about it. It's the same thing over and over again. We'll have to see what people do about it. It doesn't seem like Apple wants to budge, and now we're just going to see if the government's able to force them to do it. Yeah, anyway.
So this brings up a third question. Not can we trust CPU and RAM, but can we trust law enforcement to self-regulate?
It's a good question.
Yeah, that was a rhetorical question.
Well, it's a really good question, and the only thing I would note about this is the guy who was asking for this, the guy who's leading the charge now, is a guy named Deputy Attorney General Rod Rosenstein. And you may have heard about him in the news over the last few months. He's the person who actually ordered the appointment of the special prosecutor, the special counsel that's investigating the Russia thing and Trump. He's also the one who wrote the the letter that justified the firing of James Comey. And so you actually do have to ask a question. Like, I don't want to get all political about this, but do we have enough independence between politics and law enforcement? This guy basically was somehow pressured into ordering the firing of the FBI director. Do you trust him with all your data? I'm not sure what the answer is to that, but I don't feel too great about it. So we'll see how this whole thing goes. All right, moving on to less dramatic, exciting things. We're going to talk some more about provable security, your guys' favorite thing. We're going to talk about, okay, quick recap. Remind me what we proved, or tried to prove, very loosely, last class. Does anybody remember? We proved, I think, 2 theorems, both involving Elgamal encryption, and somebody remind me what 2 things we proved. We defined 2 security definitions. And we sort of tried to prove that Elgamal was secure under both of those. Yes?
Elgamal is secure under IND-CPA.
Good. Okay, fantastic. And what was the assumption? We needed some assumption. We couldn't just prove it from first principles. So Elgamal is IND-CPA secure under the assumption of what?
The decisional Diffie-Hellman.
Good. Under the D, I'm going to just call it DDH problem. And that was the second thing we proved. What was the first thing we proved?
That it's semantically secure.
Oh, well, that is semantically secure. Yep. We proved the second thing. Come on, guys. Don't make her like, what's that? Good. And we proved that the same thing, Elgamal is under a much weaker definition of security. Just as kind of a warm-up, we proved that it has this one-wayness property under a weaker assumption, computational Diffie-Hellman, which is basically what we call the Diffie-Hellman assumption, but we specify that it's computational. Okay? Why do I keep saying weaker and stronger? Why do I keep saying that DDH is stronger than CDH? Can somebody explain to me? Let's write these out quickly just so I can be reminded. Okay, so computational Diffie-Hellman problem is given, let's just skip the group description, given G to the A, G to the B. What do you need to find? Good, G to the AB. It's just the Diffie-Hellman protocol written out is like what you would get if you were watching two people talk. And the decisional version of this problem, DDH, similarly given G to the A, G to the B, and I'm going to call it, let's call it Q. What is the problem? What are you trying to solve for?
Q
Okay.
is equal to the random number or G to the AB.
Good. Okay, so basically that's exactly right. So we'll say 1 if Q equals G to the AB, 0 if, sorry about that, Q is random in the group. Okay? So this is our problem, DDH. Okay? Why is one stronger than the other? What does that mean? Stronger. I claim that one is strictly a stronger assumption than the other. Explain to me what that means.
For DDH to be true, CDH must be true as well.
Okay, good. So, very good. That's beautiful. All right, so if I can solve, if CDH, let's write it exactly the way you said. If DDH holds, the assumption holds, then CDH must hold. Explain to me why.
Because part of the proof for DDH is CDH.
That's pretty close. Okay, so if I had an attacker, right, who could solve CDH, we're just doing a contradiction, right? So we're saying if DDH holds, then CDH must hold. So by contradiction, if I had an attacker who could solve CDH efficiently, then what would that mean for DDH? Well, if I give you this DDH tuple, G to the A, G to the B, and I have an attacker who can solve the computational version of the assumption, that means our attacker can compute G to the AB. So all you need to do now is look at Q and say, hey, this G to the AB I just computed, is it equal to this Q? And now you've solved DDH. So in short, this one is a weaker assumption and this is a stronger assumption because, strictly speaking, this one cannot hold unless this one also holds. Does the reverse hold? Is it possible for CDH to be true, meaning CDH holds, but DDH does not? Could you show me like a similar kind of result, showing me if you had a DDH solving algorithm, that would let you solve CDH? No, there's no way I know how to do it. It's kind of weird. How would you even do that? You get like a bit. You get like a 1 or a 0 out of this DDH thing, and then how would you use that to solve CDH? I have no idea. Yes?
Just run it a bazillion times.
Just run it a bazillion times. No, there's no like known generic algorithm that does that. In fact, there are actually special kinds of groups, which we won't talk about in this class, where you can actually have CDH be hard and DDH be easy. Forget I told you that. It doesn't matter. But just this is the point. Okay, so this is it. DDH is stronger than CDH. Great, so we proved these two results. I hope you guys can, from your notes, reconstruct enough to remember those results, should you ever be asked to remember those results, because it will be important. But good, all right, so these two things, I'm not going to go over the details. Now, just one thing I want you to remind me of. How did we build this proof? How did we prove, roughly speaking, what was the technique we used to prove that Elgamal was either of these things? Just give me the high-level technique. It's a contradiction. So we assumed, what if there is an attacker who wins this security game with non-negligible probability? Then that must imply, we showed that it would imply something which is basically an attacker that would solve CDH. And what was our overall approach to doing that?
Like an algorithm.
So you'd assume that you have this
Good.
thing that can solve one of these problems, and then you use it as a sort of like a subroutine.
Yes, so assume we have a one-way CPA algorithm A, and we would build, and I like to draw this with boxes, but these boxes just represent computer programs. So we assume that we have this algorithm, and then we write another algorithm, which I'm going to call a CDH solver B, and it would take in the CDH inputs. It would call this internal algorithm A as a subroutine. In fact, it only called it once. And then it would use its output to compute the solution to the CDH problem. And so basically, we're constructing this, kind of hollow shell. This algorithm B is a hollow shell. We're constructing most of it, but the core of it, the guts of it, is this call to this one-way solver. And in reality, we don't know if such a thing exists. We're just showing if it did exist, we'd instantly get a solver for CDH because we could use that as a subroutine. And this kind of proof has a name, and I mentioned it last time, starts with R. What is it called? Reduction. It's a reduction proof. Fantastic. All right, so this is how we prove things secure. Now, we're not proving anything is absolutely secure. We're just saying if you trust this number theoretic assumption, you can trust this crypto. Maybe that doesn't hold. Maybe CDH is not. Maybe quantum computers come along and CDH is blown. And so all of a sudden we don't trust it. But if we do trust it, we can show that these things are secure. Okay, now we're going to do some funny stuff. We're going to do something that is unpleasant. All right, we're going to actually talk about hash functions. Problem we have when we start to try to argue about certain schemes is we don't know how to do this using kind of these simple, elegant proofs that we showed for Elgamal. Some schemes don't seem to work that well for these. And these are largely schemes that involve hash functions. Now, somebody quickly remind me, what's a hash function?
Maps an input to a new output.
Good. It maps what kind of input? What's the domain of a hash function?
Variable length.
Variable length. Good. Variable length strings. 1 billion bytes, 10 bytes, whatever you want. And what's the range? What's the output?
It's fixed length.
Fixed digest. Yeah, it could be different. Let's say we're talking about SHA-512. Well, you can guess what the output size is. There it is, 512 bits, okay? We would write this like this. We'd say 01 star, meaning variable length input. That's supposed to be a star. Okay, so we'd say this is H, and it would take in this thing, and it would output 0, 1, oops, that's supposed to be a curly brace. Sorry, my curly braces are bad, to the 512. And this is what SHA-512 looks like. We just call it the function H. Fantastic. So we have these hash functions. What properties do they have to have? What security properties do we anticipate that they will have? Shoot.
Irreversible avalanche property, and you want to be fast.
Okay, so you said irreversible. Explain what that is.
And if I give you a hash value, I shouldn't be able to pick what the input value is.
Okay, what if the hash value is a hash of the word kitten? Could you potentially, if I give you that hash, figure out that it's a hash of the word kitten?
If I hash a bunch of words and I check for matches.
Okay, so, but there is an attack. So how can we say SHA-512 is reversible? I'm just trying to point out that this definition is lacking a little bit of detail. Because there are things that certainly you could feed into this hash function that somebody would be able to reverse just by doing a dictionary attack. Yes?
It's many to one because of the changes in the domain and the range. So digest you got for kitten might also match with a different message.
Okay, but what if we even went with short words? What if I have a 256-bit string? Okay, now it's not many to one anymore. 256 bits to 512. Well, there could be some collisions, but probability is pretty low, right? So you're telling me that, you know, with a 256-bit input, I can't go, I can, what are we saying? Could it be possible to have a 256-bit input that's hard for the attacker to reverse? Like I compute a hash on some 256-bit random number. Can you get that number back if I do that?
Add a solve to it?
No solve, just a 256-bit random number. Do you have a strategy for going backwards from that hash?
If you have like a large rainbow table, you should be able to do that.
Not with a big, I mean,
it's going to take you a long time, but
okay.
eventually you will go there.
Okay, but here we are talking about an attacker who can't spend, you know, 2 to the very large number. So let's say a limited time attacker should have a hard time. Yes?
Remember, a DES lookup table is half a
Yeah. I think we can rule out anything that involves either a brute force search. Rainbow tables, by the way, these are just a technique for trading off some space for time and for doing pre-computation. They don't really let you do exponential time searches anymore. They just help you with searches that are kind of a little bit hard, but they don't let you do that. So yes.
Did you just like look in the SHA-512 algorithm and like?
Okay, maybe you found a flaw in the SHA algorithm that actually lets you invert it. Let's assume you have it. Okay, the NSA designed this thing. We think they know what they're doing. Okay, my basic point is when you talk about something being not invertible, being one way, when we talked about one-wayness in encryption schemes, we had a very specific definition. We got specific about what it was we were trying to attack. What was the message that was being chosen? Does anyone remember what that was? When we talked about the one-wayness encryption definition, we didn't let the attacker choose the message. We picked a message to encrypt, and then the game was, can you give me back that message? How do we pick that message? Anyone remember from last time?
Randomly.
Randomly. Okay, so good. So one-wayness means if I pick a random message of some large size, it should be hard for you to invert the hash of that message. That's all it means. Fine. What are the other things we want from our encryption, from our hash functions? We talked about a bunch of properties.
You want any change in the input to make a significant change in the output?
Yeah, that's kind of weird. Can you define that mathematically? By the way, the thing we just talked about, one-wayness, is also called pre-image resistance. And when we talk about hash functions, for some reason, we talk about pre-image resistance. You just said this thing. Define that mathematically.
So
Any change in the input changes the output.
yeah, so I think the idea is that if you flip one bit in the input, at least 50% of the bits of the resulting output should be different.
Okay, maybe we can do that, but it's kind of hard to figure out how to express that in terms of like a game, like an attacker would try to. Yes?
The attacker shouldn't be able to tell the output from random.
I like this. I like this. Very good. So the attacker should not be able to distinguish the output of the hash function computed on something from a random string. I really like that, except for the problem, which is what is that something that they computed on? A random message?
When the attacker chooses?
Yeah, does that work?
Oh, because they can just choose.
Yeah, because remember, the attacker has a copy of SHA-512. They can pick the message kitten. They can tell you, hey, compute a hash on kitten. And can they tell the difference between what you give them back and a random number? Of course they can. They know what hash of kitten is. So we're missing something in this definition. I like your definition, but there's something missing, which is that if we had some kind of secret, like if we were hashing something that the attacker didn't know and it was random and they couldn't guess it, I would really like your definition. That would be a very good definition. But the question is, we don't necessarily have that, right? Like they can hash anything they want. They might be hashing strings of their own. We want these hash functions to produce junk that looks really random and has this avalanche effect even when they know what is being hashed. It's really hard to come up with a definition for this. It's actually really fundamentally hard. So, okay, I'm going to cut through a lot of nonsense, and I'm going to give you something that is total BS. And I want you to appreciate that what I'm about to give you is total BS, and it is just a model. Okay, so years ago, and actually this kind of started with Claude Shannon, who, believe it or not, was a big, everyone who did information theory or like fundamental complexity theory also did crypto. Maybe for good reasons, maybe not. But Claude Shannon was very interested in block ciphers, shockingly. And Claude Shannon had this notion. Now, I'm not going to express this in terms of block ciphers because that's a little more complicated. I'm going to express his basic intuition in terms of hash functions. He said, let's imagine we have a hash function h. Okay, like we had before, it has some arbitrary sized input, and it produces some fixed size output. And instead of saying 512, let's just call it L bits. He said, I want to capture the notion that this is really random looking, but I don't really know how to define that. So let's imagine we instead use some kind of fake experiment. Let's say that I am here, okay, I am here, and I'm somebody running in this computing environment. And instead of having the hash function be an actual deterministic algorithm that I have code for, what if we instead create a magical oracle? Okay, inside of this oracle, we're going to pretend, and this shows up in the Ross Anderson book, we're going to pretend that inside of this oracle lives an elf. And the elf has a bulletin board. I want to be clear, I did not make this analogy up. Okay, the elf has a bulletin board, and it has basically two columns. Okay, column 1 is a message, and column 2 is the hash of the message. And this is all the elf does. When this game starts out, the elf starts with an empty bulletin board. There's nothing written on the bulletin board. When I want to hash something, instead of running a piece of code, which is what I would normally do, if I want to model this hash function as something really strong, what I would do instead is I would call out to the elf. I would say, please, elf, please hash m, some message I pick, any message I pick. I send it to the elf. And the elf does what? How does the elf compute a hash? Well, we're going to assume the elf has a pair of dice or a really good random number generator. It's perfect. This is mathematics. We can just assume it's great. Okay, I'm going to change this column. I'm going to call it message just to make life easier. Okay, so the elf is going to do the following. First, the elf is going to look at their bulletin board and say, have I already been asked to hash m before? If m already appears in this column of the bulletin board, well, the elf's not going to do anything. The elf's just going to look at the previous result that they hashed, and they're going to give us back the response. Okay, so if it's already on there, they'll just give us back whatever's on the bulletin board. Because hash functions always give you the same response. They're deterministic algorithms. We want to model that. If the elf has not been asked to hash m before, the elf is going to write m onto the left side of their bulletin board, and what are they going to put on the right side? How are they going to compute the hash? Hint, they're dice. What are we going to do?
A random number.
Good, we're going to generate a random number of L bits, and I'm going to write that as a bunch. This is my random number generator. Okay, it's probably longer than that. Roughly speaking, that's what the elf will do. And that will go into that column. It is a perfectly random number generated from the elf's perfectly random dice. And now it's on the bulletin board. The elf says, okay, great, here is your response. And this is an oracle. I can query the elf as many times as I want. If I query it on something I've already asked for, I get back the same result, just like a real hash function. If I query it on something I've never asked for, I get something that is perfectly, uniformly random and chosen from the right, 512-bit space that you would have for SHA-512, if that's what we want to model. And this is great. Now let's say there's more than one person in this computing universe. Maybe there's an adversary down here, and he's trying to break my encryption. Well, he also gets to talk to the oracle. Right? So this models the idea that in the real world, we would have a piece of code that implements SHA-512, and anybody would be able to call it. There's no secret in the SHA-512 code. Well, in this model that we're building, we've just replaced SHA-512 with this oracle, which is, this elf doing this stuff. But otherwise, the whole universe looks the same. And if there's 1,000 people in this universe, all running some protocol, they all get to talk to the same oracle. So they all get the same responses when they try to hash a value. Okay, what's nice about this world is it kind of tells us the thing that you wanted from a hash function, which is sort of that they're random, right? If I query a value that nobody's ever queried before, I'm guaranteed to get a uniformly random number. So this is an awesome hash function. As hash functions go, it's fantastic. It's also kind of ridiculous. This is not something that any real hash function can achieve. Can anyone give me an intuition why no hash function could be as good as this model that we've just defined? There is a very fundamental reason why SHA-512 cannot be as perfectly random as this elf.
It's deterministic.
Well, I mean, this is deterministic. It's modeling a deterministic function, right? If I query the elf 1,000 times on the same message, I always get back the same thing, right? And you're right. This is being chosen each time we start the game. The elf is essentially sampling a new function h. But let's ignore that. Let's say we pick a different version of
I have a
SHA-5.
question.
Yeah.
So when you throw the dice, wouldn't there be a possibility of regenerating the same hash?
Sure. What's wrong with that? Can hash functions have two different inputs produce the same output?
Yeah, but it's not going to be collision resistant, right?
Is it though? Remember, the word collision resistant, which we didn't talk about, we should remember, is not collision free. Are there collisions in a regular hash function like SHA-512?
Of course.
Of course, because there are lots more inputs than there are outputs. There's just by definition, the pigeonhole principle, there are going to be collisions.
Yes, but two dices will.
Okay, so
probably
what
be
is the
about-
probability? Let's say we query this on just two different messages. What's the probability we'll end up with a collision? It could happen. I agree with you.
1 in 36?
1 in 36, that's a lot. Oh, no, forget about dice.
Oh, okay.
They're binary dice.
Okay.
These are, by the
okay.
way, just to be clear, these are 512-bit binary random numbers.
Oh, big dice.
Okay, I'm sorry.
Big dice.
Using dice was maybe a little too poetic. What he's got is a big hardware random number generator that spits out 512 bits, okay?
I was still back there trying to figure out how do we keep the
Binary
elf in the
dice.
box and how do we
These
feed
dice
him
have
and
two
take
sides
care of
on them, and
everything
they're
else.
coins, I
We're
guess.
good.
And he flips the coins, all right, let's forget this. Okay, so he's got a coin,
What if
and
somebody
he's going to
gives
flip
the
the
elf
coin 512
clothes?
times. It's a perfect
Clothes.
mathematical coin. Let's not get
Sorry.
carried away in my elf analogy here, all right? Good. All right, so does this answer our collision problem? Yes, there's a probability you could get two different inputs that collide, but since they're long numbers, 512 bits, the probability goes up as you get more things on the bulletin board, but it's still going to be, basically the birthday bound, and that's pretty small over a 512-bit string. Okay? Good. Any other questions about that? All right, I was about to ask you guys, what are we modeling here? What kind of function? There's an actual abstract mathematical function that has the properties of this elf and his bulletin board, or her bulletin board. What kind of function? What we're doing is we're actually starting with an empty bulletin board, and we're doing something called lazy evaluation. We're creating a function. Remember, a function is just a mapping from inputs and outputs. We're creating the function over time. If we kept querying until the bulletin board was absolutely full, we would now have a complete description of some function. What kind of function would it be that we would have created? Or sampled. We are sampling a function, if you prefer, from some distribution. Okay? This thing that we're sampling, remember we talked earlier on about the notion, maybe we didn't, of random functions. Does anyone remember what a random function is? Okay, if we enumerate the set of all possible mappings, all possible distinct functions that have this, of course there's an infinite number, but even if we just map this to we stop at 10 gigs or something of input, right? We could make this finite just by having a limit on the input size. We enumerate all possible functions, and we sample one of those at random. That's what a random function is. Okay, so we sample from this function thing. Great. So what we're doing basically when we lazily fill up this bulletin board is we're sampling a random function. We're doing it lazily, but eventually we will have a random function. Okay, why can't SHA-512 be a random function? Shoot.
Because it's not lazily evaluated.
Yeah, but if we just had this elf, instead of picking it as we ask him, instead we just have him go from all possible inputs, build his bulletin board, and now we've got it. And now we've got SHA-512. Why can't that be SHA-512?
Uniformly distributed currency.
Okay, it's not uniformly distributed. I grant you that SHA-512 cannot be a uniformly distributed, the same as this uniformly distributed bulletin board. But why? What information theoretic reason is there that SHA-512 can't be like this? Yes?
There are more mappings. There's not a one-to-one correspondence between potential mappings and the deterministic and random cases.
Okay, well, I don't understand. Okay, good. Let's just talk about the size of this function, this bulletin board. If we filled it in all the way to the bottom, every possible input, how big would it be? Really big. Let's just say we limited this. Let's say we just, for make life easy, we just limit this to be the simpler version of the hash function that only has 512-bit inputs. You could do that. We could just say, hey, this is SHA-512 just on 512-bit inputs. How big is this bulletin board? We made it tiny. This should be easy. It should be a tiny little bulletin board now, right? No, there's 2 to the 512 rows in this bulletin board, and each one has size at least 512 bits, just to describe the output. Okay, so that's really, really big. This bulletin board is really big. How big is SHA-512, the program that runs SHA-512? What is the size of the description of SHA-512 in kilobytes? Okay, so this is, let's just quickly, 2 to the 512, 512 bits is 64 times 64 bytes. I'm not going to ask you guys to calculate that because it would be too big a number for your calculators to work with. It is a very, very large number, more than the atoms in the universe kind of number. Okay, so how big is SHA-512, the program?
10 kilobytes.
Yeah, like 10K. SHA-512, you could probably get it down to like 3K if you really, really like used that kind of crap that I showed you with RC4 and tried to fit it in a tweet or whatever. You could make it very small. So clearly, SHA-512 is very much a smaller, more compressed version of the function. So the question is, could you take this bulletin board, which is huge, and somehow compress it down using some compression algorithm to make it as small as SHA-512? And then you'd be great. You'd have a 10 kilobyte algorithm that would be as good as this bulletin board. Is that possible? Why not? Why?
Because you can't look up all the messages, like, if you don't store them.
Okay, you're saying, but couldn't we just run like some super good, couldn't we run like gzip on this bulletin board? Like, couldn't we make it small?
I think you can, but then you have to like unzip it again.
Even if we don't care about the computation, can we make it small? Yes.
No, because it's random data.
Ah,
You can't compress
good.
random data.
Good. This is random data. When we sample a random function, either whether we do it lazily like this elf did, or we do it all at once in the like sample from all possible functions, we're basically building a big pile of uniformly random data. And compression algorithms, no matter what you saw in Silicon Valley, like you can't actually compress random data. Maybe like you can occasionally, maybe sometimes random data is compressible, but very low probability. So basically we know there are information theoretic bounds on how small such a table could possibly be, this random table approach, right? Whereas SHA-512, definitely a lot smaller than that, right? So this is clearly not a random function. Whatever SHA-512 is, it's not a random function. Let me ask you a question. You mentioned this idea of, well, we could compress it, but maybe it would take a long time to decompress. Let me ask you a question. If this was a random function, table implementing a random function, and you were an algorithm running on a computer like a Turing machine, how long would it take you, take like someone who was actually searching through this, just to find one of the entries in the table? If I asked you to hash a number, how long would it take you to like find that entry and give it back to me, to compute the response, just looking it up in a table?
512 comparisons. Do I go to the top half or the bottom half?
Well, I
I'm
mean,
searching through.
think of it now. Let's say we're on a Turing machine where the table is now stored as a tape. How long is it going to take us? How many steps of the Turing machine is it going to take us to find the right entry in this table on average?
2 to the 256.
Yeah, it's going to take us, or even, yeah, potentially, yeah, it's going to take us some exponential number of steps to find, just to look up in this table. Forget about the size of the table. Just the computation is going to take a long time. And this is just, if you remember your automata, this is just a basic result. Yes?
Well, if it was sorted, you could do like a binary search, right? Do it pretty quick.
Even then, if you think of this as a Turing machine, right? Because you're searching basically for something that could be anywhere on your tape, you might have to go all the way to the end of the tape, and the sort's not going to help you. Right? Now, if you think of this as a modern computer memory, that's kind of two-dimensional, but even that doesn't help you. It's just going to take you a long time to look it up. This is not feasible. Okay, SHA-512 is not a random function, but it would be super cool if it could be one just for the purposes of modeling our crypto system. Why would it be? Well, let's try to actually make an encryption scheme using this ELF and show how great it's going to be. Here is what I'm going to do. Okay, remember, I am here, and I'm going to encrypt something like this. Okay, so remember, how would we do, you guys saw counter mode encryption. How would you build counter mode encryption out of a hash function? Let's try that. What would that look like? Yes?
You hash something and use that as your counter at the beginning.
Good, so we're gonna pick a key. Let's define the encryption scheme. Okay, so we're gonna encrypt under some key K a message. All right, and what we're gonna do is we're gonna do for I equals 1 to M divided by L, which is the number of bits in our hash function. We're going to compute ciphertext I is equal to the hash of what? We're building counter mode out of this this is the dumbest thing in the world. Let's say we're going to do this. How would we use a hash function to compute? So if this was AES, or a block cipher, we'd do AES under key K of some counter, which we have here, it's I. What are we going to do with a hash function? We don't have a key, we only have one input. How do we get our key and our counter into this thing?
XOR?
Could XOR them, but that might be dangerous because some bad stuff could happen. What if we just concatenate them? What if we just say hash of K concatenate I? Now we're feeding both the stuff in. This is great, right? And we XOR that. Apologize for my notation. Let's just say M sub I is the ith block of the message. That's our entire encryption algorithm. Does that make sense? Okay, so we're basically going through. We're just going to basically take every single block. We're going to feed in the key, concatenate it to the counter, hash that to get some bits, and XOR it with a block of the message. Voila, we have ciphertext. It looks pretty intuitively okay to me. Can we prove that this is actually secure over here in this world with the ELF? Okay, well, let's think about it. I am here, and I'm going to sample a key K that only I know. And maybe there's a decryptor out there somewhere. Let's not worry about them. And we also have an adversary. The adversary does not know my key, presumably, otherwise there's not much security. And so we're going to ask the question, how secure is this encryption scheme? Okay, well, let's model it. Let's take it through one step at a time. When we start the game, the ELF has nothing written on his bulletin board. Okay, what are we going to do? We're going to encrypt a message. Let's say we're going to encrypt a message M1, M2, M3. So it's a 3-block message. Just concatenations. Okay, so this is our message we want to encrypt. How do we do it? What's the first thing we send to the ELF, according to this encryption algorithm? It's right there.
K concatenated with.
Good. So our first query is going to be on K, which is our secret key. And by the way, nobody can see these queries to the ELF. The adversary can't read us talking to the ELF. It's a magical ELF. You get magic. Okay, K concatenated with 1. This is an empty bulletin board. What is the ELF going to do?
Write some random stuff.
Good. Write some random stuff. Fantastic. So they're going to write K concatenated with 1 on the left side. And they're going to put, and I'm just going to write random stuff. And they're going to send back random stuff. It's actually a bunch of bits, but my last attempt did not go well, so we're not going to do that again. Okay, so random stuff. And then I'm going to compute C1 is equal to what? I'm going to call this random stuff XORed with M1. Okay? Now what am I going to query on? What's my second query?
Is it always going to be 1?
No, because remember, it's for I equals 1 to however many blocks of data.
You're always going to start with 1.
Oh, we're going to always start with 1 here. Okay, let's just say we're encrypting one message. If we were going to encrypt lots of messages, we'd have to figure something else out. But let's just make life easy, okay? Just encrypting one message. Okay, what's the next block of message? How are we going to encrypt that? Okay, fantastic. So ditto, ditto, ditto. We do the whole thing again. And what happens here? Well, there's not going to be a collision. We've never queried on this one before. K XOR 2. We get more random stuff. This is not very formal. And then so on. K XOR 3. More random stuff. And fantastic. And so we get C1 is equal to this. Apologize for my notation. We're going to call this more random stuff. XOR with M2. And more random stuff. XOR with M3. I'm pretty sure this is not the actual notation that Shannon would have used, but we're going to go with that. Okay, so each of these strings we get back from the oracle is uniformly perfect random stuff that came from this elf's magical coin that they flipped over and over again. Okay, what does that tell us? Well, actually, there's one more thing before we get there. Okay, the adversary is also allowed to talk to the elf. They can send in a query to the elf. They can say, hey, I want you to hash some stuff for me. Okay, so let's consider 2 possible universes. In universe 1, the adversary never sends in either of these 3 messages to be hashed. Okay, and then somehow they see this ciphertext. C1, C2, and C3. So they see the ciphertext. What can the adversary learn from that ciphertext? What statements can we make about what they could possibly learn from the ciphertext? If they have never queried the oracle on any of these three messages, that is our assumption, what does that ciphertext look like to this adversary?
Random numbers.
Why?
One time, I don't know.
It's a one-time pad. Good. If the adversary can't break into the elf's house, which we're going to assume, and if the adversary never queries on either of these three messages, which we're going to assume for now, then each of the responses to that hash that the encryptor made is going to be a uniformly random string. And in other words, what we're doing is we're encrypting this message by XORing each of the plain text blocks with a uniformly random, perfectly random string. And we know the security of that is dictated by the security of the one-time pad. Basically, this devolves to a one-time pad encryption. If we have this perfect hash function, we get what amounts to a one-time pad encryption of the message. And we know there's no information the adversary can get from a one-time pad because it's information theoretically secure. However, I made an assumption here. My assumption was that the adversary never queried this elf on either of these three messages, or any of these three messages. Is that a valid assumption? Could the adversary have queried on one of those three messages?
Yeah.
Yes. Okay. Go.
Wouldn't it still not matter because they wouldn't, like, I don't know how to put the words, but wouldn't it not matter if they queried them?
Well, no, it would be really, really bad, right? If the adversary queries on this, then it knows this string.
You mean the entire thing, right?
I'm talking about k concatenated with 1. If the adversary were somehow able to query this guy on k concatenated with 1, they would get the one-time pad. And remember, the one-time pad is only secure as long as the adversary doesn't know it. It's perfectly random and kept secret from the adversary. If the adversary could query on k concatenated with 1, they would get the one-time pad. If they could query on k concatenated 2, they would get another part of the one-time pad. But all they would have to do is query on one of these in order to win or get some information about the message. So, now the question is, how can we possibly say the scheme is secure? We don't know what the adversary is going to query on. We don't know if they're going to query on k concatenated with 1 or not. If they don't query on it, we can say that the scheme is secure. It's a one-time pad. If the adversary does query on any of those values, we lose. So what can we say about the probability the adversary queries on any of those three messages? Can we say anything about the probability of that? Yes?
It's negligible.
Why?
Because we can just query polynomials times and the probability is 1 over exponential.
Good. So if the adversary is a polynomial time adversary, if they can only query a reasonable number of times, and the key space is large, we didn't really say that, but let's say the key is exponentially sized, then yes, the adversary's best possible attack is basically to try to brute force the key. They would query the hash on every possible key, and they would hope that they get lucky and they eventually query on the actual key. But since the key space is large, let's say it's a 256-bit key, and they only get to query, I don't know, 2 to the 50 times, their probability of succeeding in that attack is bounded, right? It's like 2 to the, what did I just say, like 2 to the negative 210. It's a very small probability. So their probability of succeeding in this is negligible. It's not 0, but it's negligible. They can't win except with the probability they could brute force the keys. And what we've actually shown is we have a scheme where, provably speaking, the best possible attack is a brute force guessing of the key. That's not bad. That's nice to show. Of course, we had to assume something totally BS, this random function thing, to prove it. But now we've kind of shown something interesting. Yes?
Is that the same probability that they would just guess the like random stuff that you're XORing with?
Well, remember, if they never query the oracle, their probability of actually guessing it, well, I mean, yeah, it could be. It depends how big the message blocks are. They could just guess what the message is. But remember, like, their guess would be completely uninformed. It would be just completely a guess. Here, their probability actually is not. They could get lucky and get the key. And if they get the key for one block, they could try it for all the blocks, and then they could decrypt the whole message. Okay, but basically here, the adversary, we can prove that this scheme is as secure as it is to brute force the key. Okay, so we've shown really the world's dumbest result, but we can show this in this model. All right, what else can we do with this? All right, I want to show last provable security result, I promise. I want to show you what kinds of things people actually do with the random oracle, and hopefully I'll get a chance to finish today. We'll see. Oh, by the way, I haven't told you what this ELF is called. This ELF has a name. We call it the random oracle. And we call this the random oracle model. And the model here is that, we actually all have an ELF, where we can compute an exponential size, exponential time random function. And of course, we couldn't do that in the real world because it would be too big and too slow. But in the random oracle model, we make the ELF do it for us, and life is easy. All right. Now I want to show you a scheme. RSA encryption. So key generation, I'm not going to spend a lot of time on because you guys know this. Actually, we're going to do RSA signing. Key generation is compute public key is equal to n, comma e, and secret key is equal to d. You've seen this plenty of times. The signing algorithm, does anyone remember what RSA signing looks like? Yeah.
You sign with your private key, and then you can decrypt with the public key, and if the message is the same.
Good. So the classic signing algorithm is compute the message you want to sign, raise it to the d, mod n. Well, we've already kind of shown that isn't a great algorithm because you can maul signatures, you can do bad stuff to signatures. And I think I showed you maybe another algorithm that I thought looked a little bit better, and it was this. Hash the message, and then raise that to the d. Okay, and the verify algorithm was pretty straightforward. Oops. What you do is you compute the hash of the message again, and you check to see is this equal to, I'm going to call this the signature. The signature, oops, that's a hue, not a signature, raised to the e mod n. Okay, so this is our entire signing algorithm. Okay, I want to do one more thing. I'm going to make my hash function special. It's going to look a little bit weird. And this is a special hash function, which is called a full domain hash. It takes in an arbitrary sized message, 0, 1, to the star, and it spits out something important, which is an integer between 0 and n minus 1. And we call this a full domain hash. Don't bother to worry about how we build such a thing. We do build such things. We can build them out of regular hash functions. Basically, we have something that maps perfectly into this domain of the RSA integers, anything between 0 and n minus 1. And we have this great hash function. And that's what we're going to use up here for signing. I'm going to run out of time, so I'm just going to start and sort of talk about how one could actually prove this thing secure. To finish up for today, can somebody tell me what security means for a signature scheme? What do we have a game for security for signature schemes? Everything comes down to games. Give me a game. I have a challenger and I have an adversary. What would security for a signature scheme even look like? I'll give you a hint. We would start by having the challenger generate a public key and a secret key and send the public key to the adversary. What now? What's the game? What do we want the adversary to do to win this game at the end?
Forge a signature for a given message.
Very good. So they get to choose any message. I don't even care what they forge on. Random junk. At the end of this game, the adversary is going to say, here is some message I made up. I'm going to call it M star, just for fun. And a signature, which I'll call sigma star. And they win if this is a valid signature. Okay? That's most of our definition. Is that enough? Okay, we could do a little better though.
You could have so that the attacker can ask for any number of messages to be signed, but those messages can't be M star.
Okay, I love this. All right, so for I equals 1 to, I don't care, Q, let's call it. What we'll do is I will send in a message of my choice, and this person over here, this challenger, will send me back sign using their secret key of M sub I. We'll call that sigma I, and great. So they can ask for the signature of any number of messages they want, and then they have to output a forgery, and your special condition was, to make this not stupid, was they can't just give me back one of the ones I gave them.
It has to be a new one.
Good, okay, so for all, let's just say, for all I, M sub I is not equal to M star, okay? That's our condition. Great, what's this called? We actually talked about this early on, we talked about max. We had a name for this definition. Yeah, maybe we did talk about it. We need a name for our game. What do we call this thing? It's, somebody mentioned forgery, let's call it unforgeability. We let the adversary pick any message they want to forge on. That's existential unforgeability. They can pick any message they want. And then they get to query on any number of chosen messages. So we actually call this existential unforgeability under chosen message attack. And this is the last of these nonsense acronyms that you guys will have to learn in this class, I promise. But now we have a definition. And we don't have enough time today, so the last thing we will do on this subject is next time we are going to come back to this scheme, and we're going to come back to this definition, and we are going to prove that this scheme actually meets this definition. Sadly, we will not be able to do this without some way of modeling the hash function, and the way we're going to have to model the hash function is to use our friend the elf. And it turns out we'll be able to do that, and we'll cover that next time. That'll be that. All right.